Okay, so here we get into some of the applications of integration, and I wanted to start this section, which is area, it's supposed to be area between two curves, just revisiting some things from Calc 1 in Chapter 4, where you really were connecting a definite integral to area under one curve. So we're just going to kind of start with that just to get that foundation started. So you know how to do a definite integral here, you know, the integral from 0 to 2 of x squared plus 2. I'm going to go ahead and just execute that fundamental theorem of calculus, which is, of course, I know you know, antiderivative of the inside. I'm going to evaluate that antiderivative first at 2 and then at 0. So you've certainly done this a lot, even in this class, right? 2 to the third power is 8. And then I'm going to have a bunch of zeros in here. So that whole thing goes to 0. I end up with 8 thirds plus 4, and that is 8 thirds plus 12 thirds, so that's 20 thirds. So that's a number, you know, and so the value of a definite integral is always a number. You've done a lot of definite integrals. Your answer could be a positive number, like here. It could be a negative number. It could be 0. You know, you've had a lot of different answers to a definite integral. But what I want to connect it with is this idea that it actually could represent area under a curve to the x-axis. So that's pretty much what's drawn down here. I just kind of screen captured the graph of x squared plus 1, your basic parabola. Just kind of moved up 2, x squared plus 2. So you see that graph there. And so the definite integral, you know, the limits of integration were 0 to 2. So that's what gives us our barriers of where to start and stop. So basically, the shape that I have shaded in from that function, x squared plus 2, to the x-axis from 0 to 2, it has a value of an area of 20 thirds. So you definitely couldn't rely on geometry to get this answer. You would need a definite integral because of the curviness of that parabola. You know, it's not a circle, it's not an ellipse, it's some other shape, and so we need calculus to do that. What I want to sort of dive into here is the meaning behind that. Like, where did that kind of come from? I can't reteach Calc 1, but I can give you some kind of extension, some kind of connection, right? So if I just take a look at this integral right here, what I want you to recognize is that x squared plus 2, that's a function. I'm going to call that just a random f of x, and I'll leave the dx there, right? And so you have those limits of integration from a to b. I'm just going to kind of leave those off. So this is a definite integral of f of x dx. What I'm going to do is sort of, I'm really going to come and write it like this, which is a really weird thing to do, but you developed this from really your conversation of what a Riemann sum was in Calc 1. This idea that these shapes that are really hard to find the area for, that geometry doesn't help you with, you could develop the area by doing areas of rectangles. So if I just do like a left sum in here, right? You could say, hey, I can find the area of that rectangle. Let me grab that left endpoint and say, I can grab the area of this rectangle, and so on and so forth. And so you could get yourself a pretty good approximation of the area. Certainly adding up all of these areas of rectangles are not going to give you the perfect answer of 20 thirds, but you would get close. And the point is, like, you know, instead of only using 4 rectangles, what if you use 10 rectangles? What if you used 1,000 rectangles? Then you would see all this like dead space in here kind of mitigate. And so you would get closer and closer to the actual area underneath this graph. So I'm just going to kind of extend this idea, you know, from this integral of f of x dx. Where did that come from? That came from a Riemann sum. Let me just draw an arrow down here. And so it came from adding up, remember that sigma, a bunch of values of the function and little changes of x, meaning like how wide is that little subinterval for each one of those rectangles, right? So you're adding up a bunch of areas of rectangles. It's just height times width. It's nothing fancy, right? And that sigma is the symbol that says add a bunch of those up. Now, if I want the exact area under the curve, we had that connotation like, well, If I have more rectangles, that would be much better, right? If I had 10,000 rectangles, that would be amazing. And so what you did is you said, hey, let me make that change in x, that width of each subinterval. Let's make that as close to 0 as possible. But, so really what I want to get at here is this all comes from rectangles. From taking rectangles where you're going to say, hey, let's let the width go to 0. Let's let it really be small. But I'm really just adding up a bunch of heights times a width. So in Calc 1, you kind of, go from the bottom up and say, well, this is what we're going to do. And you actually physically did Riemann sums, right? We are not going to do Riemann sums in this class, but I'm going to remind you about where everything is anchored and where it's sort of connecting to before we move forward, right? So you had these widths and the heights, and I say, oh, I want that, so many of them, I want the width to go to 0, and that's what developed that definite integral, right? So I'm just reminding you about that to try to be helpful with what we're going to tackle, which is area between two curves. So that's a little bit more advanced, right? So anyway, again, we found our area quickly. It was 20/3. It's exact. We are not going to do Riemann sums. I don't want anyone to be terrified of doing Riemann sums in Calc 2. But I want to remind you of how things were developed. All right, so again, just from the Calc 1 perspective, and to kind of throw some things in that we should be able to do, I should be able to know what the graph of the sine wave is. I want to try to describe this definite integral in a graphical sense. So I'm just going to graph the sine wave because I want to see, like, what does this actually mean? Now, the sine wave is the one that starts at the origin. It goes up to the max, to the middle, to the min, and back to the middle again. We did this in pre-calc a lot. The period of the sine wave is 2 pi, which means I could fill in all these little, missing pieces in here. This is not the best sketch, but in general, that's what the graph of the sine wave looks like, and I can visually see it, right? Now, this definite integral goes from pi to 2 pi, so I'm not looking at this section. What I want to do is highlight this section. So when you do a definite integral of sine from pi to 2 pi, you're really kind of describing what's going on here. So let's actually compute the definite integral. The antiderivative of sine is negative cosine. Make sure that we're good at remembering all of our trig rules. And of course, I'm going to use that fundamental theorem of calculus. I'm going to evaluate cosine of 2 pi, well, negative cosine of 2 pi, and then evaluate negative cosine of pi. And so cosine of 2 pi is 1. Cosine of pi is negative 1. So I end up with an answer of negative 2. That's the value of that definite integral, for sure. But I really wouldn't talk about this necessarily being area, because area has the connotation of positivity. But this happens in a definite integral when your graph goes below the x-axis. We can say, well, hey, that region has an area. The area of that region is 2. It just happens to fall below the x-axis, which is why we put that marker on there of the negative. That's how that kind of comes into play. And we'll definitely handle this a lot better in the relationship of talking about area between two curves. We can get it a little bit more direct, but just kind of reminding you, like, definite integrals can be positive, they can be negative, they can be 0, but graphically this is what's happening. If you get a negative number for a definite integral, it means more of your function is below the x-axis than above the x-axis. So good reminder there. And then just another standard question here. I'm going to zip through this one pretty quickly. This is a graph that I wouldn't expect you to graph, necessarily by hand. I'm going to try to stick to the common functions like parabolas, lines, exponential functions, some polynomials. But this would be a little bit more. And so here you can see I just gave you the graph. So this one is written in a way that's saying, hey, let's find the area of the region, which means your answer has to be positive. If it says find the area, I want a positive answer. So let's talk about what section of the graph we're going to do. It's underneath this graph, bounded by the x-axis, so that's great. It's a definite integral, from 1 to 4, and it turns out everything is great. Here's x equals 1, and well, there's x equals 4, and so I don't have any adjustment to make. Like, this is perfect. We're going to do the area underneath that particular function from 1 to 4. Okay, so again, you're really kind of taking a look at this and saying, oh, let's just think about that as that Riemann sum approach in a way, right? Like we could do all these rectangles, and really I'm just talking about the area of those rectangles, which is just height times width. Really, that's what I want to try to work on. We're going to be drawing rectangles in these shaded regions, just so we have a marker of like, hey, here's one generic rectangle in my space. Let me describe what that is. I'm going to do a definite integral from 1 to 4. That's my start and stop. And so, thinking about that one rectangle, I can say, well, the length there is the value of the function. That's your f of x. And your width is always like that dx, right? It's some small value. We're not going to put a delta x. We're going to say some really small, like little differential of x. So what we would say is a delta x. We kind of just use that dx in our definite integral notation. So this is worth doing, right? Like actually crunch the numbers on this. But as far as an integral that represents the area of this particular region, this would be it. This would be great. This would be set up. Sometimes I do that. I just ask you to set up the integral that represents the area. It's worth it for you to use your skills from earlier in this class and even Calc 1, to get through this. You should get an answer of 3/2 natural log 17/2. So this requires a u substitution. It's certainly worth it for you to go through the steps on this. And I might as well have a minute. I might as well just do it. Like this is where you're going to use all of your skills of integration just, in solving other problems. So there's my u substitution. What I think I'll do here is do that complete change of variables. You don't have to, but I'm gonna kind of decide that, hey, if x equals 4, then u is going to be 4 squared plus 1. So that means u is going to be 17. And if x equals 1, then that means u is going to be 1 squared plus 1, or 2. I can just do that complete change. I can throw those limits of integration out because they actually belong to the u variable. And so I can actually, get rid of those x's. This is great. That's where you see the 3/2 shape up, right? And I'm left with the integral of 1 over u du, which is the natural log of the absolute value of u. And here's where you see that 17 and the 2 come in, right? So I can kind of take that 3/2 on the outside and say, well, it's natural log of 17 minus natural log of 2, which I just got crafty and decided to combine that as natural log of 17/2. So this is, an application of integration. It's important that you can set them up and also that you can evaluate them.